Operating systems are collections of programs that automate the interaction between people and the computer. For example, operating systems allow people to control the operation of a computer through a terminal using easy-to-understand commands. Without an operating system, people must control the computer through the binary switches on the front panel. Also, operating systems allow people to control the flow of information within a computer system from a terminal keyboard. Without an operating system, people must move and file information manually. But operating systems require computer resources such as a large amount of memory, auxiliary storage, and sometimes specific I/O devices. However, some minicomputer configurations do not have enough resources to support an operating system. We'll examine the process of developing an assembly language program on a minicomputer without an operating system in the first lesson of this study unit. In the second lesson, we'll discuss the general functions of operating systems and show how a simple operating system can aid in the development of an assembly language program. In the last two lessons, we'll examine specific types of operating systems and their uses. A minicomputer configuration that's too small for an operating system might include a central processor with 8K of memory. It might also have a terminal and a high-speed paper tape reader and punch to allow information to be stored offline. Now let's see how a program is developed and executed in this configuration, which is too small for an operating system. The first step is to manually load the machine code of a simple program called a bootstrap into the system's memory. The bootstrap is a short program that people toggle into the system through the front panel switches, one bit at a time. Then the programmer sets the switches to the address of the bootstrap, pushes a button that loads the address into the program counter in the processor, and then pushes the start switch of the computer. At this point, the bootstrap program instructs the processor to input the loader program from the paper tape reader into memory, thus completing the initialization of the computer. In the next process, called editing, a paper tape form of the source code is generated. The first step of the editing process is to load a program called an editor into memory. The editor interacts with the programmer to generate the source code tape. When the editor is started, it will allow the programmer to type the source code into the computer. After the program has been typed in, typing mistakes and other errors discovered during typing are corrected. Corrections are typed in on the terminal keyboard, and the editor updates the stored source code and types out the updated copy of the program on the terminal's printer. After the source code has been corrected, it is punched out onto paper tape. The programmer types a punch command to the editor, and the editor instructs the processor to output the source code on paper tape. The source code on paper tape can now be read and processed by the assembler. The programmer places the paper tape of the assembler into the paper tape reader, enters the starting address of the loader through the switch register, and starts the computer. Once the assembler is in memory, Pass 1 of the assembly process can begin. During Pass 1, the assembler reads the source tape and builds a symbol table in memory. After reading through the entire tape, the assembler prints the symbol table on the terminal along with error messages for any errors that were encountered. Next, Pass 2 is performed. The programmer loads the source tape into the reader a second time, enters the starting address for Pass 2 through the switches, and starts the computer again. The assembler reads the source tape again, line by line, and generates machine code that is punched on paper tape. Now the question is, has the assembly process occurred without errors? After the source code has finally been assembled with no errors, the machine code that has been punched onto tape by the assembler is ready to be executed. Now it's time to try running the program that has been translated from source code. To do this, the programmer enters the starting address of the program through the front panel and pushes the start switch. Errors or malfunctions often occur when a program is first executed. When errors occur, a debugging process is performed to isolate and correct errors in the machine code. The debugger interacts with the programmer at the terminal to allow the person to test parts of the program one at a time and modify locations in the machine code program at various phases of its execution. The machine code program is selectively executed and modified under the supervision of the debugger until the program under test appears to function properly. Now that we have traced through the development and execution of an assembly language program on a paper tape system, turn to your workbook for review and exercises. Your workbook will tell you when to return to this program. There are many different operating systems, but they all perform the same general functions. Operating systems are collections of programs that reside in main memory and instruct the processor to load and execute other programs with a minimum of human intervention. Because most operating systems and the other programs they control are very large, a random access auxiliary storage device is usually required to hold the programs that are not currently in memory. This storage device is usually a disk. A copy of the operating system is stored on the disk in a region that is sometimes called the system area. Additional space on the disk is taken up by commonly used programs, such as assemblers, compilers, editors, and so on. Typically, a collection of these programs, sometimes called the system library, is delivered with the operating system by the computer manufacturer. The remainder of the disk is used for application programs and other files of user-created information. The name of each program file and data file on the disk is recorded in a directory in the system area. The directory also contains the location of each file on the disk and other important information. Operating systems designed to serve one person on a single terminal are called single-user operating systems. Computer systems with a large number of terminals to serve many people at once are controlled by time-sharing operating systems. On the other hand, some computer systems are designed to control and receive data from many machines. These computers are controlled by real-time operating systems. And finally, some operating systems are designed to process data that is prepared offline and is input and output through high-speed I/O devices. These operating systems are called batch operating systems. Let's look at an example of how operating systems reduce the need for human intervention in computer operations. For example, to load the editor, the programmer may simply type "Run Editor" on the terminal. The operating system then sends to the disk interface information that causes the disk directory to be sent to the memory. After the operating system discovers where the editor is located on the disk, it requests the content of that area of the disk to be loaded into memory. After the disk interface completes the transfer, it issues an interrupt to the processor. This interrupt alerts the operating system that the editor has been loaded. Then the operating system starts the editor, which sends a message to the terminal to begin the editing process. This complex loading process requires less than 1 second to perform, and the programmer can begin editing immediately. Thus, a single-user operating system allows a person to work rapidly at a terminal without getting up to handle paper tapes, as is necessary in paper tape systems. Various types of operating systems perform 6 fundamental functions in the control of computer operations. Often, operating systems are designed to be modular, with each module performing a specific function. The part of an operating system that performs the function of overseeing all operations is called the executive. The executive keeps a record of all programs that are in memory and starts and stops their execution as necessary. When a program is being executed and a peripheral device issues an interrupt, the processor transfers control to a part of an operating system called an interrupt handler. The interrupt handler saves the contents of the registers in the central processor that reflect the status of the program that was being executed. Then the interrupt handler determines which peripheral device has issued the interrupt and which program is required to service that device. The interrupt handler passes that information to another part of the operating system, the scheduler. The scheduler keeps a record of all the tasks waiting to be done in the system and decides how quickly the interrupt must be processed. The storage allocator decides which programs in memory can be moved to auxiliary storage to make room for the critical program. It also decides where in auxiliary storage these low-priority programs can be moved to. Another part of the operating system, a device handler, moves the programs out of memory onto the prepared area of the auxiliary storage device. Typically, operating systems have many device handlers, one for each type of peripheral device on the system. These device handlers control the actual transfer of information between memory and their particular devices. To find the program, another part of the operating system is needed, the library manager. The library manager checks the directory on the auxiliary storage device to find out where the desired program is stored. Then the device handler for the auxiliary storage device is used to transfer the desired program into the waiting area in memory. Finally, the executive starts the program, and the computer services the device that caused the interrupt. This concludes our discussion of the general functions of operating systems. When the machine stops, go to your workbook for review and exercises. The workbook will tell you when to return to this program. Online operating systems are designed to interact directly with the users and machines. There are 3 types of online operating systems. One type is the single-user operating system, which is designed to interact with just one user, usually a programmer. Another type of online system is a time-sharing operating system. This system interacts with many people concurrently. The third type, the real-time operating system, interacts with machines through machine-oriented I/O devices. The difference between these online systems and offline operating systems is that offline systems process information after it has been prepared carefully away from the computer. Offline systems will be discussed in the next lesson. In this lesson, we'll examine the 3 types of online systems on the basis of their general functions. The first 2 functions, the interrupt handler and the device handlers, are largely the same for the 3 types of online systems. The important point to remember about interrupt handlers and device handlers is that on many online operating systems, user-written programs can call these routines for inputting and outputting data during execution. Therefore, programmers who write programs to be run online need not write routines to control I/O devices. Now let's examine single-user, time-sharing, and real-time operating systems with respect to the remaining 4 functions. In a single-user operating system, these functions are relatively simple. The major job of the executive is to respond to the user at the terminal by loading and starting programs in the order requested. Therefore, the scheduling function in a single-user operating system is performed by the user. Storage allocation is performed by single-user systems. This function is simple because single-user systems usually divide memory into only 2 areas, the operating system and the program area. In a single-user system, the last function, the library manager, oversees relatively simple files compared to those in larger operating systems. The drawback of a single-user operating system is that computer time is not used very efficiently, because, as you know, a computer can operate much faster than a person. Therefore, time-sharing operating systems have been designed to execute programs for many users concurrently. The functions performed by these systems are more complex. The technique of maintaining many executable programs in memory and alternately executing them is called multiprogramming. In time-sharing systems, the executive multiprograms the user programs, sometimes called tasks. The decision of when to start and stop each program is made by the time-sharing scheduler. Most time-sharing schedulers divide each second into equal time intervals called time slices, which are distributed evenly among many user programs. Thus, every user program gets executed a little at a time. When the number of users does not exceed the computer's capability, no user will wait very long for output. Since execution time is being shared among many user programs, the storage allocator must arrange for memory locations to swap each executing program in and out of memory. The storage allocator must also control swap areas on the disk, where all these programs reside temporarily when they're swapped out of memory. Thus, the storage allocator in a time-sharing system swaps programs continuously. The library manager also has special tasks to perform in a time-sharing system. User files in the system library must be protected from access or destruction by unauthorized users. Therefore, the library manager must check user identification numbers, passwords, or other access codes to limit access to stored files. Now let's examine the functions of real-time operating systems. Real-time operating systems control computers that interact with machines rather than people. To an operating system, the difference between people and machines is that if it doesn't respond fast enough to a person, the person merely gets irritated and may go away until some other time when the system isn't so busy. However, if the system doesn't respond fast enough to a machine, data can be lost, or the process the machine is overseeing can get disastrously out of control. Therefore, to avoid this in real-time operating systems, multiprogramming executives are streamlined to operate very quickly. Also, the scheduler determines which program to run next depending on the urgency of the jobs to be done, rather than on the even distribution of time slices. Sometimes urgent jobs also get special treatment from the storage allocator in a real-time system. Programs that may be needed almost instantly are not swapped out, but are allocated permanent areas in main memory. Although time-critical jobs can reside permanently in memory, the library manager must still be able to locate data files for the system quickly and efficiently. Now that we have briefly discussed online operating systems, go to your workbook for review and exercises. The workbook will tell you when to return to this program. Batch operating systems are the most common type of offline systems. Batch operating systems are designed to process vast amounts of information that have been prepared offline on punch cards or on some other offline storage medium. The functional parts of batch operating systems keep the processor functioning efficiently while processing vast amounts of data. To ensure that the processor always has a program ready to execute, typical batch executives multi-program with a large number of tasks that have been previously prepared offline. The scheduler manages this input queue and decides which programs to run according to a complex priority scheme that depends on the importance of the fast delivery of the results, the amount of data that has been input for the program to process, the amount of memory and other resources the program will require during execution, the amount of time the program has already been in the system, the estimated total execution time of the program, and finally, the other control information that is input to the system with the program. The storage allocator must manage main memory and auxiliary storage space for many different sizes of programs and data files. The number of these programs and data files also affects the library manager that must access all of them. The program and data files handled by batch operating systems are frequently so numerous that many auxiliary storage operating schedules batch jobs for execution during the time the processor would otherwise be idle. Thus, foreground-background operating systems make efficient use of computers and applications where a mixture of real-time control and batch data processing is required. This concludes the audiovisual program on operating systems. When the machine stops, go to your workbook for the last set of review and exercises.